Hello GATE aspirants, welcome to GATE Chemical Solution channel. This is 1 mark fluid mechanics question in the year 2020 GATE question paper. Please read the question very carefully and identify what is given and what you have to find out. Now we will see the concept for this problem, then we will go for the problem solution. If you are well aware of the concept, you can skip the concept explanation part and you can directly go for the problem solution. Okay, this problem is related to motion of the particles through the fluid. Okay, if you consider in chemical engineering point of view, many processing steps, especially mechanical separations, that is filtration and separation of the solid dust from the gases and absorption problems, all are the motion of the particle through the fluid, right? So in such cases the fluid may be either rest or it may be moving. So this kind of treatment comes under this concept. So I have considered a solid particle in the fluid. Fluid may be either moving or it is at rest. The movement of this particle will be required some external force. Okay, let us say that is Fe. So this motion of the particle will be definitely opposite by the fluid, right? So that is the buoyancy force. One type of force is the buoyancy force. It opposes the weight of the fluid. So it is acting in opposite direction of the fluid particle motion. Similarly, the drag force also, it is mainly because of the relative motion between the fluid and particle. Okay, so this is also opposite force acting in opposite direction, but parallel to the both these two forces are parallel to the external force. Okay, actually in general, since it is a relative force, what happens, it may make an angle of with these two forces. In such cases, we have to resolve two components. We have to resolve into components. If you solve such type of problems, it will be very complicated. So for that we have considering only, we are assuming that the drag force also opposing in so in such case we are assuming that we are considering that the drag force also acting in parallel to the external force. Okay, so in such cases it is a treatment of one dimensional motion. Okay, we will see how we will get the equation for this. So suppose I have considered a solid particle of mass m and it is moving with a velocity u. Okay, so let us consider a solid particle of mass m and moving with a velocity u in a fluid of density rho. So I have mentioned that three forces are acting on the particle. The resultant of these three forces is nothing but the accelerating force of the fluid, the accelerating force of the solid. Then only the solid particle will move in the fluid, right? Okay, so that is external force and buoyancy force and drag force. These two forces are acting in opposite direction of the external force. Resultant of these three forces is nothing but the accelerating force of the solid particles. Okay, here Fe is the external force that is given by mass of the solid particle and external acceleration of the particle. So here the buoyancy force is nothing but Fb equal to is the product from the Archimedes principle. It is a product of the mass of the fluid and external acceleration. Okay, so again this mass of the fluid displaced is nothing but the density of the fluid and volume of the fluid into external acceleration. But so this volume displaced by the fluid is measured in terms of how much ever the solid volume, that much amount of fluid will be displaced, right? So rho f into volume of the solid is mass of the solid divided by density of the particle. That solid may be particle. Okay, and AE. So this can be written as Fb equal to mass of the solid particle, density of the fluid and external acceleration divided by particle density. Here this is the drag force. From the definition of the drag coefficient CD, so Fd by AP divided by half into rho u naught square. Here u naught is nothing but u here. In our case, velocity of the particle. Here AP is the projected area of the particle. Okay, suppose if you project the spherical particle, it will look as that is the projected area in the perpendicular direction. Let's say this is the particle. So let's say we are assuming it a spherical particle. If you the projected area in the perpendicular direction, the particle is moving in this direction. If you projected the particle, the area projected area in the perpendicular direction, it looks like a circle. Okay, in 2 dimensions. So that is the projected area. This is the drag force. From this drag force is given as FD equal to CD u naught square rho into AP divided by 2. Okay. So from this, by substituting these two forces in the equation 1, so we will get like this. So u naught is nothing but u. By taking the mass common from this term and this term, it will be coming here. Okay. So by taking AE common in these two terms, AE into du by dt equal to AE into rho p minus rho divided by rho p minus CD u square rho AP divided by 2m. Okay, clear? Actually this external force is either because of the gravitational force or centrifugal force or electrical force or magnetic force, but in our case we are not considering for magnetic or electrical force, we are considering only either gravitational centrifugal force. For suppose I have considered a gravitational force, in such case A is nothing but the gravitational constant, that is g. Okay, so from this equation 6, du by dt equal to g into rho p minus rho divided by rho p minus CD into u square rho into AP divided by 2m. So since g is constant, the drag force will be increasing with increasing velocity. Okay, so what happens, since this term is constant, this is keep on increasing, what happens, this if you reach one particular time, so this term will be becoming 0, right? Since all these terms are 0 constant, only the drag force will be, this term is keep on increasing. Okay, so we will reach gradually in the equation 7, acceleration decreases with time and approaches 0. So du by dt becomes 0. Okay, so at that particular time, the particle reaches constant velocity. If velocity is constant, then only this term will be 0, right? So initially the particle will be accelerating. So let's say particle, it is starting from here, it is moving towards the downwards, or if in the horizontal tube also it is moving in this direction. Initially the particle will be accelerating, it reaches again at certain point, it reaches a constant velocity. In such case du by dt will be 0, right? So that whenever du by dt equal to 0, we will attain the maximum velocity of the particle. That maximum velocity is called as the terminal velocity or terminal settling velocity. So we can also call as a terminal settling velocity. So for that, du by dt equal to 0 from the equation number 7. So from equation number 7, taking this term this side and sending this term this side, we will get ut equal to, this is called terminal settling velocity or terminal velocity, it is square root of 2g into rho p minus rho into mass of the particle divided by projected area into density of the particle, drag coefficient into density of the fluid. This is equation number 9. So for example, I have considered the particle is a spherical particle. Okay, so in such case, how this terminal velocity will be, we can calculate. So mass of the spherical particle is volume of the spherical particle and density of the particle, right? So since it is a spherical in shape, the volume of the particle is 4 by 3 pi r cube in terms of diameter pi by 6 dp cube into rho p, right? So projected area of the sphere is, I have mentioned previously, that is in the form of circle, so pi by 4 dp square. Okay, so by substituting m value and AP projected area value in the equation 9, so we will, and simplifying that one, we will get ut equal to 4g into rho p minus rho into dp divided by 3 into cd rho. So at low Reynolds number we can call it as a Stokes law region. The drag coefficient cd equal to 24 by n area of the particle. So this is the drag force. Okay, here again the n area of the particle is diameter of the particle, velocity of the particle, density of the fluid divided by mu. Okay, so in case this is the particle Reynolds number, in case of the Reynolds number of the fluid, this dp is nothing but the diameter of the pipe, not the particle. For Reynolds number of the fluid, remember this one. Okay, so by substituting this cd term in the equation number 12, so we will get, substituting equation number 13 in 12 and simplifying the expression, you will get like this. Okay, once go through all these steps, ut equal to this one. So squaring on both sides, you will get ut square here and ut here. So this term and this square will get cancelled. Ut equal to dp square g rho p minus rho divided by 18 mu. This is the terminal settling velocity expression or terminal velocity for a spherical particle moving in Stokes law region. That is n area of the particle is less than 1. This is the Stokes law region. In the Stokes law region, the cd equal to 24 by n RE. Okay, n area of the particle. So this, by substituting this one only, we will get this expression. So this is the terminal settling velocity in Stokes law region. Remember, that is Reynolds number of the particle is less than 1. So for the case of higher Reynolds number, that is n area of the particle greater than 1000 and less than 2 lakhs, the drag coefficient is approximately constant, that is cd equal to 0.44. Okay, so by substituting this equation number 16 and in equation 12, so this is the drag coefficient. No, this is the drag coefficient term in the equation number 12. By substituting this one and simplifying, you will get ut equal to 1.75 square root of g into dp rho p minus rho divided by rho. Okay, here rho is the density of the fluid, density of the particle. So this is applies the Newton's law region. Okay, clear? We will see the solution for the problem. So in the problem they have mentioned that a spherical particle and freely settling, density of the liquid is given, density of the particle is given, viscosity of the fluid is given, and diameter of the particle is given, and g also given. They have already clearly mentioned that this Stokes law is valid. What is the terminal settling velocity? We have to find out. But if at all they have not mentioned the validity of the Stokes law, Newton's law, you have to find out Reynolds number initially. Then we can identify whether it is Stokes law region or Newton's law region. Then the corresponding equation we have to apply. Okay, so already they have mentioned this Stokes law is valid, so you have to consider in this equation. So by substituting the g value and diameter value, density of the particle, density of the fluid 18 and viscosity of the fluid, and simplifying this, calculating, we will get ut equal to 5 into 10 to the power of minus 3 meter per second. So this is the maximum attainable velocity of the particle or terminal settling velocity of the particle. Okay, I hope you have understand the concept and problem. So if you like the video, please like, share and subscribe. Thank you.